Welcome students. Today we want to discuss about convolution integral. So the motivation behind convolution integral is the following. Suppose you want to compute Laplace inverse of h of s, and your h of s is a function of f of s times g of s. And you know the Laplace transform for f of s. So f of t, which is Laplace transform of f of s, is known to us. And Laplace transform of g of s is g of t, that is also known to us. So is there a connection between h of t, g of t, and f of t? Or we are asking some kind of a product rule for Laplace transform this. So is there a connection? Yes. And the answer is yes, through the convolution integral. Before we go further, notice the following, that Laplace inverse of f of s, g of s is not equal to Laplace inverse of f of s times Laplace inverse of g of s. Yeah, this can be seen by an example. So let's take f of s equals to g of s equals to 1. Then Laplace inverse of fs times gs is going to be Laplace inverse of 1, which is 1 over s, and Laplace inverse of f of s times Laplace inverse of g of s is going to be 1 by s times 1 by s. So it's going to be 1 by s squared, and these two are not equal. Yeah. So there is no reason to believe that such a simple formula will hold for Laplace transform. Rightfully so. So we'll discuss about convolution. So convolution is in some sense a generalized product. Is a generalized product. So you should look at on Wikipedia an example of how the graphic works. But let's get to the mechanics of it. So let f and g be two functions, and we want to define the convolution of these two integrals. So these two functions, f and g. So what is the definition of the convolution? So convolution h of t is given by 0 to t, f of t minus tau, g of t minus tau, d tau, which is same as 0 to t, f of tau, g of t minus tau, d tau. So these integrals are called convolution integral. And we write them, so since they're convolutions, we'll write them as f star g, and to indicate the variable t. Note that here we are essentially saying, so you can basically see that both these formulas are equal. So let's start with the first one. So in one, substitute sigma equals to t minus tau. Yeah, so we want to show that these two integrals are same. So if you look at this, it's going to be sigma equals to t minus tau. Then if tau is So in this case, if tau is 0, sigma equals to t. And if tau is t, then sigma is 0. So this is what we are going to do in the first integral. So what do we get out of that? So this implies we get tau to t to 0, f of sigma, g of, now what is tau from here? So we get, this gives me tau equals to t minus sigma. So we get tau equals to t minus, so instead of tau, I'm going to write t minus sigma. Now I need to substitute d tau, right? So what is d tau? And d tau equals to, if you look at the derivative of this, if you take derivative on both sides for this equation, you'll see that d tau equals to minus d of sigma. So we get minus d sigma. And if you use the minus sign to invert the limit of integration, you get 0 to t f of sigma g t minus sigma d sigma. And if you replace sigma with tau, because after all it's a variable, you can see that it's going to be equals to 2. So in sense, you can see here that f star g is same as g star f. So the property is seen to be commutative. Now there are a few more properties we can see of properties of convolution, namely the following. F star g, as we already saw, is g star f. Now it can be checked that f star g1 of g2 is f star g1 plus f star g2. So the first property is called commutative property, commutative law. This is distributive law, distribution of star over addition. Third is associativity. So f star g star h is same as f star. So that means if you're taking convolution of three functions, you basically can group any two of them together and then apply the third one with it. So such a law is called associative law or associativity law. Fourth, f star g. So f star 0 is same as 0 star f, which is 0. That is a property of 0 or 0 property. And what is 0? 0 is basically a 0 function. Yeah? 0 is a 0 function. Yeah, so this is what I mean by 0 here. Now, so this can be seen as some properties similar to the multiplication. So we can see properties similar to multiplication. However, there are few properties which are different from multiplication, namely one. So one, f star 1 is not equal to f. What is my 1? My 1 is an identity function. Yeah, like say for example, 1 of x is x for all x. Yeah, this is what 1 means here, okay? Because this all thing, these all is happening in the space of functions. So this is not true in general. And second properties, f star f is not necessarily positive. Now note that the outcome of convolution is basically a function, right? So not necessarily positive means that the f star f is a function whose output could be negative as well. So these are the properties different. So these are the properties different from, so difference compared with regular multiplication. Okay. So now let's look at an example of a convolution. So we want to compute convolution of e and 2t, cos of 2t. So here let's take f of t equals to e to the power minus t and g of t equals to cos of 2t. Now let me recall the formula. So we have the formula is f star g at t is 0 to t f of t minus tau g of tau d tau. Okay. So then let's compute this. So therefore f star g of t is 0 to t e to the power minus of t minus tau g of tau, which is cos of 2 tau d tau. So now we want to compute this integral. We'll have to use integration by parts. So integration by parts. So first one, we'll have u equals to cos 2 tau dv equals to e to the power minus t minus tau d tau. So the integral becomes, so what do I get from here? So this implies du is minus 2 sine 2 tau d tau, and v is integral of this, so it's e to the power t minus tau. Now integration is happening with respect to tau, right? So it's going to be, so coefficient of tau is what? 1, so division by 1. So therefore we get, if I call this as I, let's call this as I. So this is my I. So my I is equal to e to the power uv minus v du. So u is cos of uv, which is cos of 2 tau minus, call uv, so e to the power minus t minus tau. Again, the limits of integration will always also be there, minus v du, which is going to be 0 to t, v is e to the power t by tau, du is going to be minus 2 sine 2 tau d tau. So let's put the upper limit and the lower limit. So when you put the upper limit, you get cos of 2t. So cos of 2t and e to the power minus t minus, so e to the power 0, which is 1. And then we get, when you put 0, so this becomes 1, the first part. So this becomes 1. And when you put 0 here, we get minus t. So this is going to be e to the power minus t. And then the remaining integral, so let's bring plus 2 out. So we have plus 2, 0 to t, e to the power minus t tau, t minus tau, sine of 2 tau, t tau. Now we have to use integration by parts again. So again, in this part, use integration by parts. By parts. So in that case, again, we'll have u equals to sine 2 tau dv equals to e to the power minus t minus tau d tau. So this implies du is 2 cos 2 tau d tau, and v is going to be same, e to the power minus this. So now let's work on finishing this integral. So we have, again, we'll have cos of 2t e to the power minus t, and this is your I, plus 2 times. So uv, which is sine of 2 tau, v, which is e to the power t minus tau, limits are from 0 to t, minus integral of v du, so 0 to t, sine of, so we get what? We get u, so we get uv minus v du, so it's going to be u is 2 cos 2 tau d tau, and this whole thing is multiplied by 2. So therefore we get I equals to cos 2t e to the power minus t. Now when we put the upper limit, we'll see that becomes sine 2t, right? So we get sine 2t, and this will become t minus t, which is 0, so sine 2t. And when you put 0, you get 0, minus, now let's take 2 out, and then this 2 and this 2 will multiply, so you'll get 4. So just keep this bigger bracket clear. So we get 4, 0 to e to the power t minus tau times cos of 2 tau d tau. Now this is same as I. So when you bring it on the other side, we get I plus 4i, which is equal to 5i, is cos of 2t e to the power minus t plus 2 sine 2t. So therefore, I is equal to cos of 2t minus e to the power minus t plus 2 sine 2t, the whole divided by 5. And that's the answer. Okay, so this is how the convolution of e to the power minus t and cos 2t is. So let's prove this major theorem. Again, this theorem is about connecting. You are given h of s, which is a function of fs times gs, and you want to compute Laplace inverse of this product. And Laplace inverse of this product is h of t, where h of t is given by f star g, where what is my f? F is Laplace inverse of f of s, and g is Laplace inverse of this function. So this is what the result is. So let's prove it. So We start with h of s first. So what is h of s? H of s is f of s times g of s. And that by definition is 0 to infinity of f of t e to the power minus st dt. And g of s, well, it will not be same t, so we have to use a different. So 0 to infinity g of u e to the power minus su du. Yeah. So now we get, so now this becomes equal to, I'll start from here. So now this is a number after all, right? Once you compute it, it's a function. It's a function of s, not number. It's a function of s. And then it can move inside here because this integral is a function of t. So by linearity, this can move inside. So this becomes u equals to 0 to u going to infinity, g of u. And then we have for t going from 0 to infinity. So this is about t, f of t. And then I can combine these two together. So I get e to the power minus s of t plus u. And then I have dt, the whole t. Okay, so now, so we have written this as, so we write it as, so this is an iterated integral. Now we'll do a transform. So let v be t plus u. So then we get, then this implies t equals to u minus v. And we get dt equals to dv for fixed u. Right. So inside this, u is fixed. Inside this integral here, u is fixed. Okay. And then u changes outside, right? So we get what? So we get this, and therefore we have this integral h of s can be seen as integral 0 to infinity g of u. We have replaced now this thing here, so we get integral u. So note that here also when t is 0, so we should write that down, t equals to 0 would give me what? V equals to u. So I'm doing a transformation for the inside integral. And when, if t goes to infinity, v goes to infinity as well, right? So we get the following. So we have u to infinity as well. F of, now what is my t? T is u minus v. So u minus v. Now this will become t plus u is v. So this becomes e to the power minus sv dv du. Okay. So now let me rearrange this a bit. So this is going to be 0 to infinity g of u f of v minus u e to the power minus sv dv du. Now we can change the limits of integration as follows. So let's see. So So the original integral looks like this because you have t, and t0 is same as u minus v0, and that is same as basically this line. And you're letting, if t goes from 0 to infinity, that is same as saying that this goes to infinity here, right? So this is how the graph looks like. Now this was your original integral, and now u equals to 0. So we need to now change the order of this integral. So let's change the order of this integral. So what we had was basically, so first we had u to infinity. So u goes from 0 to infinity. So u is going from 0. So sorry. So first integral was u to infinity. So first your v. So how does your v looks like? So first you hit v. So this is your v. So first you have u. So if you look at this integral, this is first your v hits u equals to v. So first it is this one, and then it keeps going to infinity. Yeah, so v is going to infinity in this direction. And then the integral for what is the possibility for u? U goes from 0 to infinity. Now we'll change the order of integration. So now instead of that, we'll first start with so we want to write now first, we want to write now u v. So we want to interchange this order of integration. So first you will hit 0, and then you will go all the way until what? So you're looking for u. So u changes from u equals to 0 to u equals to v. So the integral will change. So it'll be u equals to 0 to u equals to v. And then we have, so I should have written this u to infinity here. So u, and then, so u hits from 0 to u equals to v. So I'm changing the order for u. And then what happens? Then what about your v? V changes from 0 to infinity. So this is going to be 0 to infinity. Yeah. So generally the idea is, what if you want to integrate with respect to, if you want to integrate with respect to v first or u first, you shoot an arrow in the direction of u. Yeah. So first curve it hits is u equals to 0, and the second curve it, while coming out it hits is u equals to v. Yeah. But note that this is a simple region. There are more, if the region is complicated, then you'll have to do a bit more. But this region is simple enough. So you have u equals to 0 to v, and what about your v? Your v changes from 0 to infinity. Now we can write down the whole thing as g of u. So the inside part will come as it is, g of u f of v minus u e to the power minus sv. So now we'll change the integral bit. So this will be 0 to infinity e to the power minus sv, because essentially this is the inside integral is with respect to u. So v is a constant, so it can come out 0 to v g of u f of v minus u du, and then whole of this dv. Now, if we recognize this guy, this is essentially, this is a convolution of g and f. That is, it is g star f or f star g, whatever you want to write it. They are, it's commutative. It's the same, right? So this is equal to. So now I'm going to replace this. So this becomes 0 to infinity e to the power minus sv f star g of dv. So now this can be seen as, can be seen as Laplace transform of, this can be seen as Laplace transform of what? F star g, right? So, and if I want to write in the notation of h, this is sv h of t, h of v dv, right? So this is, so the connection is made. The connection is that h of s is a Laplace transform of ht, where ht is f star g of t. Okay. So therefore the connection is made. Now we can use that to find out Laplace transform, Laplace inverse. So all you need to do is so let's look at the following problem. So this can be thought of as Laplace transform, product of Laplace transform of two functions. So the step is recognize, so recognize this as product of two functions. Whose Laplace inverse we know, okay? Whose inverse Laplace transform is known. So you can write your f of s as g of s times h of s. And we know Laplace transform of where g of s is 1 by s plus 1. We know the Laplace transform of that. And h of s is s upon s square plus 4. So we know the Laplace inverse of these guys. We know to use formula from the table. So use formulas from table. So formula, the numbers are 2 and 10 as well. You can have a look from the table. Namely, so we get what is the Laplace inverse of this guy? So g of t, which is Laplace inverse transform of g of s, is e to the power minus t. And h of t is Laplace inverse of h of s, and that is going to be cos of 2t. So now third, we need to compute. So what is Laplace inverse of f? So Laplace inverse of f of s is simply f of t, where f of t is g star h or h star g, whatever, whichever one you think is simple enough to compute. So this is going to be 0 to t g of t minus tau h of tau d tau. This is going to be 0 to t e to the power t minus tau cos of 2 tau d tau. And this convolution integral, this integral was already computed. At the start of this lecture. Yeah, so if you go back, you can see that we computed already the convolution of e to the power minus t and cos of 2t, and we found out it to be this guy. So therefore, we can have f of t is 1 by 5 2 sine 2t plus cos of 2t e to the power minus t. So this is the Laplace inverse transform of this function. Now, one more interesting application of convolution integrals are when you're using the Laplace transform to solve initial value problem with an arbitrary forcing function. Means you're given this g of t and you're not specified what this g of t is. So let's look at the following example. So notice that this is not specified. So the idea is we will basically solve it with general g of t, and whenever the need be, depending on different kind of functions, you can have you already have a solved work done, and at the end you just have to substitute g of t. Okay, so that's the idea. So let's work on this one. So first step, take Laplace transform on both sides. So what is Laplace transform of y square is s square y of s. I'm using the usual notation, so I'm not rewriting, but in case y of s is Laplace transform of y of t, and g of s is Laplace transform of g of t. All right, so we get s square minus s of y0 minus y prime of 0 and Laplace, so that's going to be 4y of s equals to g of s. Yeah, your g of s is not small gt is not specified. So now let's work it out. So from these two guys, I can take y of s common. So what is left? Y of s is times s square plus 4 minus s of y0. What is y0? Y0 is 3. So 3 minus y prime of 0. So that would be 1 equals to g of s. Or a little rearrangement can show you that this is going to be 3s minus 1, bringing this on the other side there, divided by s square plus 4 plus g of s times s square plus 4. So now we want to compute Laplace inverse of this functions now. So this can be written as, so first 3 times s upon s square plus 4 minus, so I'm going to transform this part into minus 1 upon s square plus 4, but if I want to make connection with sign, I'll need 1 over 2. So multiply and divide by 1 over 2 plus g of s upon s square plus 4. Okay, so now this is going to be, let's look at this guy. So Laplace transform of this guy, so now y of t is going to be, so now it will be Laplace inverse of this part here. What is Laplace inverse of that? That is 3. Laplace inverse of this is cos of 2t e to the power 0, which is 1, minus half, for this part is going to be sine of 2t plus, Now, what about g of s? So g of s can be thought of as, so Laplace inverse of g of s upon s square plus 4. So now notice that g of s can be seen as multiplication of Laplace transform of two functions. Yeah, so it's half s squared. So we'll convert that into s squared plus 4 times g of s. So this is what this part is equal to, right? So let me rewrite that again. So y of t equals to 3 cos 2t minus half sine 2t. Now this part, L Laplace inverse of g of s can be seen as 2 upon s squared plus 4 half times g of s, right? So this is what my g upon s squared plus 4 can be seen as. So now when I break it, it's going to be the convolution of half. So this is what, what is the Laplace inverse of this guy? Laplace inverse of this guy is, so just this part here is Laplace of sine of 2t. So just this part. So now this will become integral 0 to t. So what are the two functions? So one function is sine of 2t. So I can write this as f star. I can write as in bracket sine of 2t star times g of t. Okay, and now if you want to write this as integral, we get cos of 2t minus half sine 2t plus half 0 to tau sine of 2 times t minus tau g of tau d tau. Okay, so this is what, so this is the setup. Now here you work with an arbitrary forcing function. So the idea is 1, so we already taken 1 for the Laplace transform, so let's work it out. So 2, once the forcing function g of t is chosen, once the forcing function g of t is chosen, we only need to calculate the integral, right? Rest is basically calculated already for us. All right. So in some sense, this will be useful to study one class of function or one class of differential equation where the homogeneous part remains the same and the forcing function keeps changing over a period of time. All right. So this helps you to understand all of them in one go to calculate the integral. Yeah. Possibly, it could be possible that you're doing it possibly numerically. So possibly numerically. Yeah, either there's a possibility you may have to use numerical methods to find y of t. Now, third important point is the first two terms. What are the first two terms? These two terms. So the first two terms are independent of g of t and only depend on initial conditions, right? Only depend on initial conditions. Yep, they are solution to what? IVP, the homogeneous IVP y double prime plus 4y equals to 0 with what condition? With y of 0 equals to 3 and y prime of 0 equals to minus 1. Yeah? Yeah. Now, and then the third term, which is here, is independent of, now this term here is independent of the third term is independent of the initial conditions, right? So the third term is independent of initial conditions and only depends on g of t, and only depends on g of t. So that's the idea. So again, let's go through this again. So 3 and 4 happen in general. So 3 and 4 happen in general. So what is the idea? The idea is the following. Consider the following initial value problem. A y double prime plus by plus cy equals to g of t with y of 0 equals to y naught and y prime of this is this. Now we take the Laplace transform on both sides. So you'll see that a s square plus bs plus c y of s plus a s plus b of y naught minus a of y naught equals to g of s. Now what we have is your y of s can be split into two parts, phi of s plus psi of s. Now where your phi of s is the part corresponding to the homogeneous part, right? So this is going to be as plus b y naught plus a y naught prime times as square plus bs plus c. Now note that this part depends only on the homogeneous part, right? So it only depends on this part here, right? It only depends on this part. And then we have the other part. So this is my phi of s and my y of s is psi of s is g of s upon as square plus bs plus c. And this can be seen as what? This can be seen as g of s times h of s, where h of s equals to 1 upon as square plus bs plus c. So now we have phi of t equals to L inverse. So let's use the big phi notation for this one here. So let phi of t be inverse of s and phi of t be L inverse of psi of t. So let's use big psi here as well. Yeah, just to distinguish them. of s, and then you get your solution y of t is phi of t plus psi of t. Yeah. So you see, the whole process can be broken in the following way. Now, and what do you know about phi of t? As we had in the example, phi of t, so this function phi of t is independent. This function is independent of g of t. Yeah, it depends on what? It depends on differential equation and initial conditions. And is a solution to homogeneous IVP. So it's a solution to homogeneous IVP. What homogeneous IVP? You basically take this IVP here and you basically put g of t is 0. That's about it. So what is the IVP then? ay double prime plus ay prime, sorry, by prime plus cy equals to 0 with y of 0 equals to y naught and y prime of 0 is some other number, y prime naught. Now, what about your phi of t? Your phi of t is, sorry, psi of t is Laplace inverse of psi of s, which is inverse of g of s times h of s, which is going to be g star h of t, which is going to be 0 to t h of t minus tau g of tau d tau. So, and again, you have that phi of t, this function phi of t is independent of the initial conditions, right? You can see that from the formula. So it is independent of the initial condition, right? Here. And the only thing it depends on is, depends on g of t and values of a, b, and c. So that's the idea. Now let's discuss this bit further about the same thing. So what happens if, so let's simplify the situation when we have y0 equals to y0 prime equals to 0. And let's take g of t to be special function, the direct delta function. So then we have g of s is going to be L of this function, and we have already seen that L of this function is 1. So in that case, what do we get? We get y of s is phi of s plus psi of s. Using the notation from above, this is going to be 0. Why? Why is that part? Why is phi 0? Because notice the following. It depends on what? What is your phi of s? The numerator has initial conditions in it, right? So y0, if y0 is 0, and if y0 is 0 and if this is 0, then the whole thing becomes 0, right? So we get this will become 0 plus g of s times h of s. This is your phi of s, and that is same as h of s. Why? Because this is equal to 1. So therefore we get what? Y of t equals to h of t. So that is That is what? That is h of t is a solution to IVP subjected to unit impulse force. That is, we can say that h of t, we will give it a name, we'll call h of t is known as impulse response when the forcing function is, so when the forcing function is the impulse function, unit impulse function, you get a solution to this differential equation, which is called which is known as, so this is the definition, is known as impulse response of DE, of the DE. Thus, what do we get? Thus, phi of t is precisely convolution of the forcing term of function g of t with impulse response h of t. Yeah, why is that? Because since psi of s equals to g of s times h of s. Okay, so let's recap very quickly what we have done. So we solved, so we started with the idea of convolution of two functions, f and g, and we saw that how they are connected with the Laplace inverse transform in this IVP here. So we proved it. What is the connection? Namely, the connection is that if you take f of s, g of s, then this can be written as Laplace transform of h of t, where h of t is the convolution of f and g. Then we basically worked on an example to find an inverse Laplace transform using convolution. Then we tried to use this to solve a general IVP where the forcing function is arbitrary. So we got the solution into two parts as sum. One part is the function, which is one part of the solution depends on IVP, and the other part depends purely on the forcing function. And then we worked on to solve it. Then we discussed the special case when g of t is direct delta of t, and then we see that in that case we have a forcing function as an impulse, unit impulse function, and the solution is called impulse response. And so that's about it. Thank you for your attention.